Hello everyone and welcome to 3DPrint.com today. We are hosting a special sponsored webcast with Dr. Stephen Rudisell from HP. Please welcome me and joining Stephen. Take it away.
Okay. Hi, everybody. Good to be talking. This is going to be a variant of a talk I gave recently at Westech, which is a manufacturing trade show. And so mostly what I'm going to be doing is kind of walking through some of the business aspects, what HP is interested in doing in 3D in the market and transforming 3D printing and additive manufacturing, how MJF plays a role in that. I'll give an overview of some other 3D printing technologies and kind of do a compare and contrast between MJF and existing technologies on the market, kind of give you an idea of where we think our advantages are and how those work. And then I'll talk a little bit about our kind of road mapping efforts as we go into the future. I already got a question before this about some developments that I myself was not actually aware of, but it means that it opens up things I can talk about because they've been publicly announced. Part of the issue that I have is that I'm in R&D, so I know a lot of things that we're working on, but unfortunately I can't disclose all of them because they have to be publicly announced by higher ups in the company first. So some of your questions, if you have more detailed ones, I'll have to kind of be a bit fuzzy on some of the answers, specifically around timelines. But we'll work through it. As we go, we'll just get started here. So HP's kind of vision for 3D printing is to drive what we call the next industrial revolution. So if you think about the history of making objects, prior to the Industrial Revolution, everything was kind of handmade and hand designed, which means everyone in the world, you know, if you were a person who made things, a craftsman, you had the ability to design it completely yourself. As we move to more industrial fabrication, the designs that were made had to match the tooling that people had to actually make those things. So you had more design kind of got moved out of the hands of the craftsmen and into these specialized, you know, engineering people who knew how the machines worked and knew how the parts could be made. And that's pretty much been the model for how we've made parts for the past 250 years. We have, the tools have gotten more specialized, the design tools have gotten more specialized. If you look at, you know, this chart from the Industrial Revolution to the Internet era, we have the ability to transmit designs very quickly. We have 3D modeling tools that allow us to make designs more efficiently, but they're still kind of like, it's a specialized field. I'm sure several of you have mentioned that you're materials engineers and designers, and you're very well aware of how difficult some of those software packages are to use and learn. They require special training. So right now we have more. The level of blue that you see on this chart is kind of charting the democratization of design, the ability of many people to design objects. And it gets better as you get better training on the tools and the tools become more intuitive. But what we're hoping to move towards this next industrial revolution is to have true democratization of design, which involves involving several people, entities who are not just HP, and working on building a software network and a design framework that allows 3D design and the ability to move parts into 3D manufacturing, to make those easy to use and freely available to everyone. At the same time, the interest is also to move the technology into at least access to this easy-to-use technology towards everyone's hands. So where we are today is kind of in between this Internet era and this 3D transformation. And part of what HP is hoping to drive is that 3D transformation. And MJF is a significant part of that, which allows us to produce parts, you know, faster, and additionally to start to move 3D printing more into the final part production space as opposed to simply prototyping. So there are several advantages that come along, you know, several future things that we hope we'll be moving towards. But I'm going to throw up this chart right here. it's similar to something that HP's done before. We have experience in driving this analog to digital transition. This curve that you see is essentially looking at cost per part, and we've previously used this in our large-scale digital presses. So if you look at analog press making, or if you want to print a large number of brochures or something, there's an analog technology that works very similar to injection molding, for example. It takes a lot of upfront cost to produce plates or representations of what you're trying to make. But then if you want to make 1 million of them, the cost goes down because you gradually amortize the initial cost. And you can defray it by selling a large number of materials or getting a lot of ad revenue from brochures that you print. The difference between that and digital printing is that the costs are higher for digital, but the cost is flat per part. You have, in the case of a digital press, for example, you have a bunch of inkjet print heads. They have a fixed cost per drop printed on per square centimeter of paper. And 3D is very similar to this. If the analog curve is the injection molding curve. Essentially, you have a lot of upfront costs that come in when you build a mold, when you have to revise a mold and get your part working exactly the way you want it and have it work on the tooling, and then you defray those costs by selling a large number of parts. In the case of 3D printing, and this is true, I think, of all the technologies mostly on the market, there's a fixed cost per gram of part that you actually make. And the shape of the part, or the complexity of the shape, doesn't actually impact the cost. But right now, as you can see here, we're able to print some number of parts, but it's not actually competitive with analog unless you're printing a very short run or a very small number of parts. If you're printing a large number of parts, there's kind of this break-even point, and then it gets worse. And in those cases, you'd still do the molding process. And that's one of these economic things we have to break through in order to move 3D printing from a prototyping or short-run manufacturing technology into what we hope down the future will produce technology that is competitive with analog at high part volume. And so as we move to that future, we're hard at work developing what we need to do and to enable this, and we'll see if we get there. But primarily that comes from two different angles, and one is just improving the productivity, the speed, the energy efficiency of the technologies we sell and have, and the other is kind of working with the materials market and improving the cost effectiveness and moving towards a more open materials market, which I'll talk about a little bit in more detail, I think, later in the talk. One of the other advantages of this analog to digital transformation that we get here is that I spoke a little bit about the complexity of the shape not mattering, and that means we can get there are particular high-value applications where having the correct shape is the most important factor. The example given right here on the left is a helmet, essentially, for toddlers or small children who have cranial deformities, and they can be reshaped by printing a special helmet and having it put on. But it has to be tuned to the shape of the head of the child's head. So there are lots of things in the medical space and in other spaces where having the correct shape has an extremely high value premium, and that's where we exist now. Things that are unique, things that are difficult to make, and things that don't necessarily need to be mass scaled. When we accomplish this digital transformation, we can actually move those unique things into mass production, which it doesn't really happen right now. If you're going to buy something at Target, you're going to get something the same thing, or Walmart or some retailer, you're going to get pretty much the same thing with limited customization. And then there are economic advantages as well as when we move to this digital transformation, is that we can significantly reduce transportation costs potentially, in the sense that for most printing aspects, you'd manufacture something, and you'd go and have a printer in a location, and you'd print it, and you could sell it near the demand. You basically have, rather than distributing a set of warehouses or something, you have a printer in any particular location, print the object you want when people order it. So rather than having a supply near a demand, as you see there, you can find the demand, produce it on demand, and then limit the amount of needing to have like a centralized facility where you make these objects and then ship them to different locations. Additionally, you get speed and waste advantages because you have the material already. You don't have to make the mold, install the mold, clean the mold, etc. So there are lots of advantages moving there. So that covers kind of the economics. If you have any questions on that section, I'll do my best to answer them. Obviously, keep in mind that I am an R&D guy. So feel free to post in the chat. And I'll move on to a little bit of a comparison between different 3D printing technologies. For those of you who are engineers, this may be kind of basic, but hopefully you'll learn something or a few new pieces somewhere. So what is 3D printing? You hear us talk a lot about digital transformation and all these kind of corporate buzzwords, but what 3D printing fundamentally is a general solution to manufacturing. Manufacturing is something that we kind of have specific solutions for. We tailor particular molds or particular pieces to create shapes. And what this is a solution that allows us to do kind of whatever we want within certain limitations, but hopefully we'll improve those limitations as technology improves. What it is a way of making parts of any shape without needing molds or machining. And machining is kind of traditional, is one of those traditional prototyping methods where you take a large block of material and then cut it into the shape you want. That's subtractive manufacturing. And this is essentially additive manufacturing, where you start with small pieces of material and kind of push them together in different ways to make the material you want. It allows you to make several different types of parts and different shapes, different geometries, and there are also several materials that are available in various technologies, from polymers to metals to ceramics. And each of the technologies kind of have different applications, and some of them have material limitations and other limitations, and I'll try and talk through some of those here. I gotta get my slide mover. There we go. Probably the most common 3D printing technology is known as material extrusion. It's kind of a family of technologies. It's commonly known as fused deposition modeling or fused filament fabrication, FDM or FFF. And the mechanism for material extrusion is essentially a hot glue gun, as you see on the left, plus a robot, which is Wally right there. And what you get there is you have a little extruder, which is a hot tip, and you push a filament through that hot tip and it melts as soon as it hits the nozzle. And then you have a robot controlling the motion, and that robot will simply draw a shape that you desire over and over and over. And every time that you finish drawing all the things in one particular 2D slice, you'll then drop a platform or raise the robot and move to the next layer. The way that all of these technologies work is they take 3D objects, a 3D model that you would make in modeling software, and then cut it into a bunch of 2D slices with a different Z thickness. And so then the printer will then take that information and turn it into a series of 2D images, and then print in one Z layer, and then another Z layer, and then another Z layer, and so on and so forth. So the advantages of material extrusion is that you have there are several materials you can use. It's very open. It's very cheap to do. Most of there are several of these printers online. If you're going to buy a $300 3D printer kit, it's going to be this, because the other technology is kind of more complicated. If you just have to put a hot glue gun with a robot, it's not so complicated to put together. You do have some strength problems with anisotropy. So because each layer essentially is melted and then solidifies when it goes down, and then you're putting molten material on top of a already solid layer, the interface between those two layers can sometimes be pretty weak. So it's difficult to get strength in a particular in a direction. So you have weaker parts in Z and stronger parts in XY. let's see. So we'll move on to some other technologies. There are several. There's a class of technologies called SLA, which are all based on stereolithography. And what this is I'm a chemist, so this is kind of it's cool to me because it's basically using a 3D printer as a chemistry set. This is kind of a UV cured polymerization. So what you have, instead of having an already made polymer, you start with the monomer pieces, and you have a big bath essentially of pre-resin of a monomer. And then you also have a curing agent in that resin that activates when it's hit by UV light. And so then you have two different versions of this. You can either use a masking technology like a DLP projector, which essentially has a bunch of little shutters that open and close and allows you to put down, to basically expose the areas of the bed or areas of the resin pool wherever you want, based on the pixels, based on which shutters you open and close. The original version of this technology had a UV laser and a mirror. Those are still in use today for manufacturing, so both technologies are available. And essentially you get slightly better, you get the advantage of these technologies is mostly accuracy in your Z dimension. So fused filament fabrication, or FDM, fused deposition modeling, the hot glue gun plus the robot technology, that it has a problem with controlling the size of the glob you get. There's kind of a sweet spot to be in where you don't get too much overmelt or too much extra material coming out, and versus the speed of the robot, those things have to be optimized. And so you can get you're kind of limited in your Z-dimensional accuracy. SLA allows you to get very fine layers and good, basically good representation of the object that you wanted to get. Accuracy to the model, essentially. In the case of strength, you still have some problems there because, of course, every layer that you make in the technology, you fuse the polymer, and then you're trying to fuse new you create the polymer where it is, and then you simply try to basically make new polymer that attaches to the previous polymer, which doesn't always work the way you want it to. And so you can have some challenges there as well. These printers, I think, are coming down in cost. They were originally pretty high, but they're starting to move them into the more consumer space. I think I saw one recently that was sub $1,000, but it was at a trade show. So don't quote me on that. Thanks. Let's see. Moving on, there are several laser melting technologies, and this is kind of one of the ones that you'll start to see that's not polymer based. It can be polymer based, but can also utilize other materials. And so these are laser melting technologies where you have a high power laser and then a bed of material. Now this one is a departure from the previous two, because there's something about the other two that I haven't talked about, and this is a good time to bring it up. For SLA and for FDM, if you have parts that you're building and you suddenly have an overhang, so you have let's say I have a part that's shaped like this, like it's an L, okay, and I'm building from the bottom to the top. This material right here is going to appear out of nowhere with no support. There's no platform to build it. And so if you're building a part layer by layer and you suddenly have material appear in midair, you have to have essentially a support for it to actually be produced and not collapse or fall down or disappear into your resin somewhere. So frequently what FDM will do is they'll have two filaments. They'll have one that's water soluble, and so they'll build a support, and then they'll build the actual part, and then you'll rinse the part afterwards, and that will remove the support, and then you have the part you wanted to make with all the correct dimensions. In SLA, they'll also have a similar, like a water soluble polymer, or they'll build support material alongside that. With laser melting, or SLS or DMLS, in this case, you have a bed of powder that you start with. You can see it here. This I don't know if my cursor goes through, but if you see that lamp in the bed, all the white space around the lamp is actually polymer. and that's basically a bunch of powder pieces of polymer. And so in this case, in the case of SLS, one of the advantages is that the build material is the support. As you build a material up, the powder that you don't fuse ends up supporting the rest of the build. Now, the way that this works is basically the same idea. You have a 3D part that you split into a bunch of two-dimensional slices. In this case, you start with a platform that has no material in it. You have a bucket that's full of material. I gotta get my hands so I can actually see them. And then every time you build a layer, the platform that has the bed will go down. The platform that has supply will go up. And you're basically rolling or spreading material across with each layer. And then what will happen is a laser will draw the two-dimensional image of your slice on that layer. Then you'll spread, and then you'll draw another layer that'll fuse to the previous layers beneath it. Advantages here are around material strength. The hardware is very expensive, but it does get you closer to injection molded properties. One of the issues, though, is that it's slow in a particular way. So FDM has this same challenge in that it's a point-based process. If you want to, you have to actually draw. In the case of FDM, you have to deposit material at each point you want to deposit it. In the case of SLS, you actually have to draw each area. And so this also works for metals. So if you basically use a metal powder and a higher powered laser, you can get higher melting temperatures, and that allows you to produce metal parts. But the technology is pretty much the same. Now, I bring up SLS and DMLS last because they're probably the most similar to MJF. We use a very similar powder handling system. So that system with kind of two buckets or a powder supply and a powder bed, we're using very similar materials and we're using a very similar system as far as powder handling. The difference is with MJF, is that instead of using the laser, we've replaced the fusing system, the system that actually melts the powder, with inkjet print heads, one of which is absorbing energy, and one of which is helping us control heat and surface finish. And we will coat, well, I'll start from the left side. We'll coat a layer of material over here. We'll then print on that layer, and wherever we print, the black drops that you see there, those are kind of radiation absorbers. Those become the part. And then we expose the layer to energy. And the areas that are black, I kind of use this as like the analogy here is like wearing a white t-shirt in summer versus a black t-shirt in summer. The black t-shirt heats up more. And so you get, if you have all these, this wherever you've printed your black t-shirt, essentially, that heats up more, and that allows you to get the powder over the melting point. And then those areas melt, and the areas that are not printed on don't, and that finishes your layer. Now, that might sound kind of like, well, what's the advantage? I'm doing the same thing as the laser. But the cool part about this is that the process by which the print heads move across the bed is actually quite fast. And it doesn't matter how much you're printing. So if you have an XY plane that has a lot of material in it, like let's say I was printing just like the whole bed, I wanted to fuse an entire cube. I wouldn't actually do that. But just for the sake of argument, if I wanted to do that with a laser, I got to draw every single point on that bed to fuse the whole cube. If I want to do that using MJF, I simply have one swath where the print head goes across and it prints all the areas at once. A lamp goes across, fuses all those areas, and you can just imagine it takes significantly faster. So what MJF does is kind of uncouples print density to speed. Now you have basically, no matter what your print density is for a particular layer, you have the same print speed going across. So right now we have the build materials we use are polyamides. There have been some questions already. I noticed a couple of them about different materials that are available. Right now, what's available on the market is a PA12, and what's coming is a PA11. I can't give dates on any of these things, but we are working on other materials, which I'll talk about here as we go. All right, I got a couple more slides on this. Yeah, so this is kind of what the printer looks like. the selling point we have here is, it's up to 10 times faster at half the cost. That depends on your build density. If you have higher densities, the speed advantages will be better. If you have lower density, speed advantages are different. But it also allows you to have lower cost per part, and we think our agent system works pretty well. There are a lot of future developments there that I'll talk about at the end of the talk that are pretty cool. The other thing that we're kind of offering at HP is an end-to-end solution. So we don't just sell you the printer; we sell you a build unit. There's actually the front panel, the biggest panel in the front, is actually a door that opens up, and you can see the build unit in the middle. That's a rollable trolley that comes in and out of the printer system. And so you can, if you get like 2 of these trolleys, you can actually have the thing operating all the time. So you pull one trolley out when you're done building, you fill it in this processing station, and you put that trolley in, print it, pull the trolley out, go over to the processing station, throw it in there, it'll cool it down, and meanwhile you've got another trolley that's just been processing for the time you're printing. So it does allow you to go for a kind of 24-hour operation cycle if you would choose to do that. One of the things that the business people like to talk about is the open materials platform and what HP is doing here. Traditionally, most 3D printers have had kind of a lockdown powder supply. You have a powder that kind of comes, it's branded, and it comes from the company you buy your printer from. There's kind of an exclusivity there, and we're interested in engaging several of the people who are making polymers and trying to figure out through technological advancement, joint work, business development, all sorts of things, to try and bring down the cost of powders, bring many powders into the market, and figure out how we got this. So these are all people that we're partnering with. These are people who are the kind of the big players in making polymers. BASF is the largest chemical company in the world. Evonik and Arkema are both megaton producers of various polymers. So we're working with a lot of high power people. And our strategy for kind of addressing this market is we want to build a wide portfolio of materials, and that is not where we are today. We're working on bringing those things to market, and there will be more materials coming, but dates are fuzzy. We're going to drive reduction of the powder and printing cost on the technology side and from the business side by trying to enable as many players as we can. And then additionally, the voxel level capabilities to enable digital fabrication, that bottom point is probably the coolest thing from an R&D perspective. I'll talk through kind of the advantages that depositing liquids in the bed can give you. What we're doing with this open platform, this materials innovation platform, is we have several different ways of putting powder into the system, and I just kind of want to explain why it takes a while to bring things to market. We don't have a fully open platform. That arrow on the right, where if you just shove any powder into the system, if we were to do that, it's very easy for you to break the printer and then blame us. So there's kind of a void your warranty issue with having any sort of powder, because we've tested several, and there are lots of materials compatibility things, and you can't always design the system to be fully open because some powders simply don't work. So we have a system where we're co-developing with several of these people to brand powders, and so those will be released and sold through HP. And we're also working with several powder suppliers on a certified system where we would take a powder that they produce, make sure that it prints, make sure it meets a set of specifications that allows so that we can assure you that the powder will work, and that will allow different powder suppliers to bring those things into the MJF market and platform. And so that's our open platform idea. So we have kind of certified powders and then branded powders. The materials roadmap here, this is no dates. There's the x-axis here is kind of amorphous. The y-axis is on quality or specialty of the materials. So right now where we are is this PA12. What's coming is PA11 soon. We're going to be building an elastomer set of materials. We'll have some polyamides where we've modified them with different fillers to allow you to get different mechanical properties. Also some other properties like flame retardancy. Things we're looking at are other polyamides and on the higher end of cost or specialty, and then high performance materials as well. And we'll also be looking at the lower end, the more commodity side of the market, where we look at thermoplastics and commodity plastics down the road. But the technological challenges of developing those things are they're present. So we have to. There's a lot of work to be done to enable these materials. I can't stress how much the R&D work that goes into qualifying and making sure these materials work. Okay, so let's get into the kind of the future ideas here. The ability to deposit agents into this powder bed is it's a really cool one. We don't just have to supply a radiation absorber. There are lots of different things that we can put into fluids that could end up going into materials and then modifying their mechanical properties. Here's just an example. If you had an ink that contained a nanoparticle dispersion, you could deliver those nanoparticles to the bed and then change the properties of the material. Whether those properties are catalytic, if you have some sort of activity in those nanoparticles that you want to capture, if you have just mechanical reinforcers, if you have something that interacts with the polymer in some way, these allow you to basically put those down wherever you want them. And that's the really cool part, is that if you want to make a composite material, we can do that. We can take a nanoparticle. You can make anything you want. You can mix it with another thing. But the cool part here is that you can take a part and you can say, I want this particular region, one small area, to have a certain type of property, and I want this other area to have a different type of property. And that's not something that's easy to do with traditional production methods, such as injection molding. If you want to mass produce a part, it's going to all be made out of the same stuff, and then you're going to take another piece and smash it together and screw it in or attach it in some way. Here, the parts will be actually fused, and you'll be able to get a particular voxel, which is essentially a three-dimensional pixel. You have this 2D slice, then you've got a Z dimension to your pixel now, and you can fill that in with a material and give it a property you want, and then have another part right next to it that's got a different property, but it's all still the same piece. Some future technologies, kind of examples of things that you might be able to do with this in the future, would be things like functional color parts. So that's parts that are strong but are still highly colorful, and we can basically deposit agents in areas all over the place that have different colors. We can get a high degree of color accuracy. So the other things we could do potentially is if we're printing something like conductive traces or metal nanoparticle dispersions, we can actually print conductors or wires into your part. So that might be an advantage there in the sense that you could have smart parts where you have a set of sensors or conductive bits that actually do some logic. Or one of the cases that we've printed is a strain gauge. In the future, you could print a set of conductors or wires or circuit diagrams into your part, and then just have like a spot that you put a chip in. You can actually just put a piece of logic there, and it'll actually be able to detect when it fails or what kind of stresses it's being exposed to, thermocouples, all sorts of things to figure out what the parts actually are, and enable kind of more of the digital data tracking on actual manufacturing hardware. Additionally, there's an idea we can produce secure parts. We can print security inks that are invisible or can only be detected by certain radiation. You can have unique identifiers that allow your parts to be tracked and traced. And then one of the other things that's interesting is you could have something like a color indicator. You have, say, a part that has like color on the exterior. Let's say I print a gear like this gear right here, and it's red, right? And as I use the gear, as I plug the gear into some machine, and as it's doing its thing, I'm running the machine, and over time that gear will wear down. And it would be pretty cool if I didn't have to wait for the gear to break and then the whole machine to get shut down for a long time, and then I've got to like repair whatever happened downstream. I could just go in and check every so often and look, is the gear black on the inside? Or is the gear blue? Did it change from red to, did the teeth wear away so that the red's no longer there? It allows you to see that a part has failed before it actually, catastrophically destroys whatever your piece of tooling is. So those are kind of some examples of what we can do. I'm really excited about this technology. I think I managed to get to the end. Yes. So thank you for paying attention. I went a little bit long, so 35 over what I said. That's good, though. We have
yes, we do.
plenty
and
of time
we actually
for questions,
have
right?
a ton of questions, so we've got some good stuff to discuss. Yes, definitely. I think we should have
try to get through as many as
some
we
of
can.
them are quite technical, so bear with me as I'm going to actually post them in the chat again, just to make sure that everyone can see what the questions are. So let me post this first one here. Now it's from Amadou, and they asked, when do you think elastomers, thermoplastics, like TPU, will be able to...
Do you want me to just read the questions? So
yeah, go ahead. You see I have it posted in red, so everybody can keep an eye on it.
Yeah, sure. Yeah, sure. So when do we think elastomers and thermoplastics like TPU will be available on the MJF? I can't give any details on schedule. I can tell you that we're working on them. Will they be compatible with the color 3D printer that was announced at the securities analyst meeting? Thank God that thing's been announced. I've been sitting on it for a long time. So to answer Diego's question right away, we don't have color yet. We do not have color yet, but we've been announced that we have a printer that's coming out that will enable color. Will the thermoplastics be available? I don't think I can say anything about the material availability on launch, but they will be eventually worked in. The materials flexibility is something that is kind of it's not going to be like a one and done kind of idea. We're going to be rolling over time as we talk to new suppliers and new materials, and we'll get people engaged. And we have to do our work on this on our end to enable those materials. So there's always some time lag involved in that.
Great.
So
yeah.
that gets through that one.
Sorry about the story. I should have practiced those words before I tried to ask them. Okay, so there are a couple follow-up. Here's another one. What is the typical power of the laser in the DMLS? Okay.
I wish I knew. Unfortunately, I'm not a DMLS expert. I know that it's higher power than the plastic ones, but I'm sure if you went and looked on, I'm sure that's spec'd out there. If you went and looked at some DMLS suppliers or talked to them, they can give you an estimate on how much power.
So I have another question here from Suzanne. How does HP plan to help reduce the cost of 3D printing?
So I talked about it a little bit in the talk about basically having multiple suppliers in the market. That inevitably means they'll have to compete with each other, and so that can bring down costs. We have several things in our hardware that we're going to be working on as far as improving efficiency, spreadability, all sorts of things on how well the machine works together. There's lots of space for efficiency and speed improvements, but we kind of have to work through that.
So I have another technical question. So what I'm going to do is post it in the chat again. Make sure that I don't fumble over this. It will be posted in red, so if you'll take a look at this one.
Sure. Okay, different types of materials on the same machine. So one of the tricky parts of the powder bed technologies is that you can't isolate particular areas. Right, you have to have a bed that's relatively uniform, and usually that means one material or a consistent blend of materials, a composite that's homogeneous. The way that we propose dealing with that, if you have different spaces or properties down the road, right? This voxel technology idea is that we can modify the properties of a material already. So if we want to make an area softer, we can potentially add agents. Now that technology does not exist today, but again, it's part of our future efforts. and trying to get that ability to produce different material properties right next to each other. That's something we're actively developing and very interested in working
So
on.
I have another one here. Is the unfused powder left after the printing after it is printed, is it reusable?
Yes. There's a recyclability factor that's developed for each material. Some materials are more recyclable than others, but the things that we've released right now, and this is a problem in SLS largely, but we are aiming to make every powder that ends up on our system to be completely recyclable within some number of generations, and that's spec'd in the sheets for the different polymers that end up being released. But yes, the goal is to have zero, as little waste as we possibly can. There's inevitably some waste that can't be recovered because there's frequently powder that's attached on the outside, and there's a post-processing area frequently used as a sandblaster. This is used all the time in SLS. You have a material that's used for final finishing of the parts, and you blast off the excess material. That material can't be recovered. But it is a very small fraction.
I do have a follow-up question. I see that just got posted in the chat. Can you use the same fusing agent and detailing agent with different materials? And how easy is it to switch materials?
Yes, you can use both. With and I think any material there's the constraints around which materials are able to be used is generally, it's not constrained by the fusing system, though there are some edge cases. And then let's see, how easy is it to switch materials? I think it's as easy as buying it and putting it into the build unit. Just to be clear from the previous question, it's not really feasible to put like two different materials in at a non-homogeneous way and still expect to get the same properties because they have different melting points or different rates of fusion or energetics, things like that.
I'm going to actually start posting these in the chat just because make sure that we stay together here. So is the unfused powder, wait, I already asked that. Sorry, I copied the incorrect one, so here we go. So the HP, multi-jet fusion, does it use multi-beam laser array?
No. The heating unit that we use is a lamp, essentially. It's a high-powered incandescent lamp. So it's a broad spectrum of radiation.
Here's another one. How does the post-process part removal compare to the SLS as far as reclaim and speed?
As far as post-process, I think it's pretty similar. It's the same idea, right? You have a part, and you have some junk on it left over from the process. You have to remove it. The rates and technologies that you can use will be very similar.
So we did have this question here. I'm going to go ahead and post it. It was from Diego. We did get an article posted as a response, but I wanted your definition on what open materials platform is.
Okay, so the open materials platform, I think there was another associated, I saw this go by. The open materials platform is simultaneously an idea that we have, it's a theoretical concept that we have a bunch of materials that are available, and people who are making materials are making them for our process, and we don't have like kind of a heavy hand in like who's doing what or who's involved. That will open up as we go. But what it also is I think what was kind of alluded to in the question after this was that it's a standardization process. Essentially, it's a way of we define a set of specs for what the powders need to be in order to work in the system, and those specifications are under development. They're not rigid or fixed yet because we're learning about this technology as well, right? We're trying to figure out how to best implement it and make it work. And so it's a set of standards that would say, like, this is what the powder needs to do or be in order to work in the system. Here you go. You can sell you some hardware to check if it works, and then develop the powder, and then you can sell the powder once we certify it.
Okay.
But yes, it's a standardization
now I see that there are
essentially.
some people actually posting in the chat now with questions. Let's start with Smith here. It sounds like fun area to work in for postgraduates. Are there lots of opportunities within HP to join the R&D team? What would be the
Yes, so it's expanding. There are I don't obviously have like job postings, but the best way to get in touch with somebody is to use the hp.com/careers website. I think that's right. I don't want to. But if you Google search HP careers or HP jobs, there's a job application site, and if you're interested in working on us, there are jobs that are posted. If you find something that has 3D in it, you can think about applying to it depending on your experience and education level and so on.
Does that look right? Quick Googling on
yes,
my part. So I got that up for you
probably
guys. Yes, thank you. So a few follow-up questions here. Okay, is warping of parts a factor in MJF like SLS?
Yes, it can happen, but I don't know if we have a spec on it. It is a challenge that we occasionally run into in R&D. We attempt to make sure that our production machines obviously don't have warping issues, but there are some edge cases where it can happen, depending on geometry, depending on other things. So we'll there are some technological challenges, but I don't see warping as like a huge problem in our released products. It's mostly something that we deal with when we start developing.
Here's
new
another
things,
one.
new powders, etc.
How do the speed and strength of HP's 3DP technology compare to the continuous DLP printing of clip printing? Let's see that there.
Yeah, I don't have a good spec on what clips speeds are, and I don't want to get in trouble. My impression is that they're comparable, but honestly, you'd have to go look at the spec sheet for MJF, go look at the spec sheet for a clip printer, and there should be kind of like a build volume per minute thing, and I don't have the clip one in my brain. I actually have the spec sheet for the MJF printer over here, but to do a comparison, I'd actually need the numbers, and I don't.
So there's a very technical question here, so I'm going to let you work through it. Here, let me copy and paste that. There we go. It's about the radiation absorber. Oh.
Yes, it's a heat transfer agent. It is not a photo initiator.
So here's another one. We keep getting tons of great questions, so bear with me as I'm trying to work through these. So here's another one. So Larry asks, he would like to jump from plastics to metal. Earlier this month at the HP Securities Analyst meeting, they stated that in FY18, HP will announce a new metal printing platform. Will this platform be MJF based? And are you able to expand on the metal powders that will be available?
So I don't work in the metals area. What I can say is that yes, it will be MJF based. The technology is different than our plastic technology. There are some significant changes. I can't really speculate as to what those changes are. And the metal powders, I don't know, man.
That's okay.
I have no information about it, unfortunately.
So here's another one. Is the fusing agent the only material holding the other powder together?
Okay, so this is a common misconception. The fusing agent does not contain a binder. There's another technology there called binder jet. I don't think I talked about it, but it's very similar. And you have in the case of binder jet, you're actually printing into a powder bed, and you have glue that you're putting down, some sort of epoxy or a material that binds things together. The fusing agent in MJF does not contain a binding agent. There's no binder. What it is a radiation absorber, and so what happens is when you print it on a voxel, that voxel heats up and melts the plastic in that area. So you're not actually adding anything to the system aside from a material to turn the area into a radiation absorber?
So a follow-up is, what is the density of the material?
PA12, for example, solidified is around 1 gram per centimeter cubed. And that's densified. I think in the bed it's it's less than that because it's actually powdered and there's a bunch of air
another one
in the
just
system as
before
well.
that. Sorry, I almost missed it. The sample parts I have seen are both black and a lighter shade of gray. What is the natural color of the material?
The natural color of PA12, for example, what's on the market right now, is white or slightly yellowish. The black is because of the radiation absorber, right? So we add into the system something that'll actually absorb the light and turn it into heat.
Okay. Now, Genevieve just asked, can you elaborate on what voxel is?
Yeah, so a voxel, I kind of glossed over a little bit in the talk, so thank you for bringing this up again. So in screens or printing or two-dimensional images, a pixel is like one addressable unit of arbitrary size. If you have printers that are given, they have like a DPI rating, that's dots per inch. That's that's basically defining the size of the pixel that you're actually making. So those can have various things depending on what they are. If you have pixels on a screen, it's the same deal. They have some resolution that's defined by the actual hardware, but what it means from the software perspective is it's the minimum addressable unit. It's the one place where I can say, I want this to be a color, and the whole pixel is going to be that color. You can't have like a pixel. If I could put multiple colors in a pixel, my pixel is actually smaller than I think it is. And so in our case, when we're printing on paper in 2D, for HP's existing printers, we have a pixel is a spot where that's the size of the drop that gets put down on the page. Now, in the case of 3D printers, it's the same idea because they're printing material, but it's still a 2D. Each slice is a 2D image, so you're printing a pixel. Now, the pixel you put down is no longer just sitting on the surface of the paper. It's very, very thin, and the thickness doesn't matter in the case of 2D. In 3D, the thickness does matter, and it has a dimension, and we have to control that dimension to make sure that the parts end up, consistent, and each layer is the same size. So now we have, rather than a pixel where you have X and Y that are of a given dimension, you now have X, Y, and Z, so you have volume. So it's actually a cube. So now you have a volumetric pixel or a voxel. So I think that should go through. If there are follow-up questions on like what voxel means, feel free to ask them, and like what it can actually do in the printer. But I can address those.
Okay, great. Before I post another question from the queue, I see Victor asked. Someone asked about backwards compatibility. Will the current machine always support the future materials, or at least plastic ones?
Yes and no. It depends, right? So the hardware, there are hardware limitations. Some materials require like a lot of heat and and may require a new fusing system. Some materials may not be compatible with our existing agents. We haven't tested all of them. There are lots of things there's a whole world of chemistry that we haven't been able to address in our kind of small like PA12 right now world. So I can't guarantee that future hardware is gonna have compatibility. We are trying to do as much as we can to make sure that future material developments are developed for pieces of hardware. But I'll have to leave it to the business team to communicate what those things are and when they happen. But I can tell you that due to the complexity of the technology and the complexity of trying to get these materials all to work together and just chemistry in general, there may be specialty materials that require specialty hardware down the road, but I don't know. That's just speculation on my end.
So we may not be able to get to all of these questions, so let's really quick here. Carlos posted, are there issues with bubbles or voids in the process or the products?
So in R&D we see some edge cases. Again, there are issues. We try to make sure that the bubbles and voids that end up in the released products are not impacting mechanical properties, or they don't exist. It's something that we're actively characterizing and trying to ensure that all of our released products do not have any sort of mechanical defects. And so as we find those things and get data, we try to address them in various different ways.
So here I'm going to post a question that was in our queue. How precisely can you, or how do you control the movable platform in the build unit?
I'm not an ME, so I don't actually know what the particular mechanism is that controls the build unit, but I can say that the spec sheet defines our precision on Z to be, let's see, with the higher end model, it's 70 microns to 130. You can pick whatever Z dimension you want between those layers.
So how does the orientation affect part strength?
So there is still some anisotropy. There's anisotropy in every technology. We think we got a pretty good way of minimizing it. And so Z is always the hard dimension across any 3D printing technology. Whatever the layer that you're building, that's always the hard one. Those ones are always going to be weaker because you're always attaching material to existing material in some way. I think things like SLS and MJF tend to do a bit better job because you're actually melting the material, and you can actually address the underlayer by, your heat transfers down and actually can partially melt the material underneath. I can tell you our goals are to get to fully anisotropic parts, and we're moving in that direction.
So let's see. Compared to other 3D printing materials in general, what do you foresee the biocompatible materials with MJF materials? See some Quan. We'll see that.
Okay. I'm honestly not sure how to address that one. We're kind of it depends on what you mean by biocompatible. Several of our existing materials are USP Class 6 certified, so they're fine for compatibility with biological systems. But I'm not sure what the as far as future looking. Biochemistry is not my my goal, so I don't actually know. I'm not in that space, unfortunately. I'm not a regulatory person or a a marketing guy kind of focused on the bio.
James just asked, in terms of what is cost, if you see his most recent one, it looks pretty technical, so I don't want to try and stutter over it.
Oh, okay. Cost differential between material costs and standard injection molding with versus 3D printing. Okay, yeah, I'm not familiar enough with the actual injection molding cost structures to speculate or provide an answer here.
That's okay.
My apologies.
You don't have to know absolutely everything. So there's lucky enough for you. No,
I feel bad when I can't
actually, speaking of that, I was wondering if there is a way that our participants would be able to follow up with you in about any of these questions here. Is there somebody they could contact? Like, is there an email address to reach out to, anything like that?
Yeah, I should get that for the next one. I'm I'm not sure who the appropriate contact is for technical specs. I think Suzanne is in the chat. Suzanne Lassen's one of our marketing people, and so she could probably put people in contact with the right if they're interested in purchasing or thinking about getting a piece of the technology. Then she can put them in contact with the right salespeople or the right communications people.
That's great. I did see from my colleague that we'll include something in the follow-up email for everybody who's listening in. So we'll have a way for you to contact if you have follow-up questions here. So thank you so much, Stephen. We do have to wrap up. We just have a minute left. So thank you so very much for your presentation and answering all of these really wonderful and very technical questions. So I appreciate you working through this with me. So thank you.
Yeah, thanks everybody.
Yeah. thank you. Steve,
Appreciate
go
you showing
ahead and
up.
come off audio and video if you'd like, Stephen. So yeah, everybody, please thank Stephen for his presentation today. It was very wonderful. Before I let you go, I do want to thank HP for sponsoring today's session with 3dprint.com. So thank you, everyone.